Welcome back to AI.Code.Cast. Today, we're going to be taking a deep dive into something called palindrome partitioning.
Sounds kind of scary.
It kind of does, right?
Mm.
But I promise it's going to be fun.
Yeah, it's a classic problem, but it's also a really good illustration of how, like, different approaches to solving a problem can lead to, like, wildly different, you know, levels of efficiency.
For sure. And, that's something I think that any coder, or really anyone who loves just a good brain teaser, can appreciate.
Absolutely.
So before we get too far into this, though, let's just, level set and make sure we're all on the same page.
Yeah, good idea.
What exactly is palindrome partitioning?
So basically, you're given a string of characters, and the goal is to figure out all the possible ways that you can split that string up into smaller chunks where each of those chunks is a palindrome.
Okay, so if we took a simple example like the word ob,
Yeah.
how could we partition that into palindromes?
Well, you could split it into 3 single-letter chunks, A, B, because any single letter is technically a palindrome by itself. But you could also group the first 2 letters together to get A, which is also a palindrome, and then you have like a B chunk left over.
Oh, okay. I see how this is working.
Yeah, so there's 2 possible partitions already.
Okay, so it's like finding all these little hidden palindromes inside of a word and then figuring out all the different ways you could combine them.
Yeah, exactly.
Okay, but I mean, why is this problem so important in coding? And it feels kind of like a word game.
It might seem that way at first, but it actually has some pretty cool real-world applications, especially in fields like bioinformatics and cryptography.
Oh, okay.
Yeah, for example, in bioinformatics, analyzing DNA sequences often involves identifying palindromic patterns.
Wow. Okay.
And in cryptography, understanding palindromes can be really helpful for things like code breaking and, designing secure algorithms.
Wow. Okay, so it's got a pretty wide reach. Okay, so where do we even begin tackling a problem like this? What's the most straightforward way to approach it?
Well, I think the most intuitive approach is usually what we call brute force or backtracking.
Okay, backtracking.
Yeah, and it's kind of like exploring a maze, You try different paths, and if you hit a dead end, then you backtrack and you try a different route.
Okay, so in our palindrome maze,
Yeah.
then what would each step forward look like?
So each step would involve adding a letter to our current chunk and checking if that chunk is a palindrome.
Okay.
So for example, if we had the string ababa, we would start with the first letter A, which on its own is a palindrome.
Right.
Then we add the next letter B and check if ab is a palindrome.
Okay.
It's not. So we backtrack, we discard that B, and then we try adding the next A instead.
Gotcha.
We check if A, that's a palindrome. So we continue down that path.
Okay, so I could see how this could eventually get us to all the valid partitions, but it also seems like it could get pretty messy and repetitive, especially for longer strings.
Yeah, you're absolutely right. Backtracking can be very computationally expensive because you might end up checking the same substrings over and over again as you explore different paths.
Right, so it's like we're wandering through that maze, but we don't remember any of the paths that we've already tried.
Exactly.
We need a smarter way to explore.
Yeah.
What if we kept track of the palindromes that we've already found?
Okay.
So we don't have to waste time checking them again and again.
That's a great idea. And actually, that's the core principle behind a more efficient technique called dynamic programming.
Dynamic programming.
Yeah, it's all about breaking down the problem into smaller overlapping subproblems and storing the solutions to those subproblems so we don't have to recalculate them over and over again.
Okay, so it's like creating a map of the maze as we go.
Mm-hmm.
So we don't keep going in circles.
Exactly.
I like that.
Yeah.
Okay, so how do we apply dynamic programming to palindrome partitioning then specifically?
So instead of blindly trying every single possible combination, we can actually build this lookup table, often called a DP table.
Okay, a DP table.
Yeah, to store whether a particular substring is a palindrome or not. So if we encounter that substring again while we're exploring different partitions, we can just look up the answer in our table instead of redoing the whole calculation.
Okay, that sounds incredibly useful.
Yeah.
But how do we actually build this DP table? I mean, it seems like we'd still need to check all the substrings at some point, right?
Yes, but we can do it in a systematic way that avoids that unnecessary repetition.
Okay.
So we start by filling in the diagonal of our table because we know that any single letter is a palindrome by itself.
Okay, that makes sense. So each cell on the diagonal represents a single letter substring.
Yeah.
And we just mark it as true.
Exactly.
Okay, what happens next? How do we start checking the longer substrings?
So then we move diagonally upwards in the table, considering substrings of increasing length.
Okay.
And for each substring, we check if it's a palindrome, and we mark the corresponding cell in our table accordingly.
So, for example, if we're looking at the substring ABA in our ABABA example,
Mm-hmm.
if we already know that B is not a palindrome because it's marked false in our table, do we then just automatically know that ABA is also not a palindrome?
Not necessarily.
Right.
In this case, ABA, I-S, a palindrome, even though the single letter B in the middle isn't.
Oh, interesting.
Yeah, that's an important nuance to remember. The inner substrings don't necessarily have to be palindromes for the whole thing to be one.
Okay.
What we do need to check is whether the first and last characters are the same, and if that inner substring excluding the first and last characters is also a palindrome.
Oh, okay. That clarifies it.
Yeah.
So we're basically like building this DP table from the bottom up, using information about smaller substrings to figure out if the larger ones are palindromes.
Exactly.
Okay, this is already feeling much more organized than that backtracking approach.
Yeah, definitely. And once we filled out this DP table, it actually becomes this like powerful tool for our backtracking algorithm.
Right.
We can actually use it to quickly check for palindromes as we explore those different partitioning possibilities.
I like it. So dynamic programming, it's all about being strategic with our calculations and storing those results so we don't have to do them again.
Exactly.
Okay, but how much more efficient is this compared to like that brute force backtracking? Are we talking about shaving off milliseconds, or is it like more significant than that?
Oh, it's much more significant than a few milliseconds.
Okay.
Dynamic programming can actually turn a potentially exponential time solution into a polynomial time solution.
Whoa. Okay, break that down a little bit further. What does that actually mean in terms of like how long it takes our code to run?
So with brute force backtracking, the number of operations our code needs to perform grows exponentially as the length of the stream increases. But with dynamic programming, the number of operations grows at a much slower rate, typically like proportional to the square of the string's length.
Oh, wow. So for really long strings, then dynamic programming could save us a ton of time.
Exactly.
It sounds like a game changer, but is there a catch? I mean, nothing in life is free, right?
Yeah, you're right. There is a trade-off. So while dynamic programming saves us time, it does require more memory to store that DP table.
Right.
The space complexity of dynamic programming for palindrome partitioning is also proportional to the square of the string's length.
So we're trading space for time, which is often a good trade in computer science.
Yeah.
But I'm curious, is there a way to like maybe get the best of both worlds? Like the speed of dynamic programming, but without the extra memory cost?
That's a fantastic question, and it leads us to another really interesting approach called optimized backtracking with in-place palindrome checking.
Optimize backtracking with in-place palindrome checking.
Yeah, but before we dive into that,
Okay.
let's maybe pick this back up after a quick break.
Okay, sounds good. We'll be back soon to explore how we can squeeze even more efficiency out of our palindrome partitioning solutions.
Sounds good. So we were talking about how dynamic programming can really speed up those palindrome partitioning solutions, but it comes with that extra memory cost of the DP table.
Right. Yeah, and we were just about to see if there was a way that maybe we could keep that speed boost but not need quite so much memory. You mentioned optimized backtracking with in-place palindrome checking.
Yes.
What is that all about?
It's kind of a technique that combines the best of both worlds in a way. So remember, in the basic backtracking approach, we kept checking if substrings were palindromes over and over again.
Yeah.
And then with dynamic programming, we stored those results in a table to avoid all that repetition.
Right. Yeah, that was the key to dynamic programming's efficiency.
Exactly. While optimized backtracking with in-place palindrome checking takes kind of a different approach. Instead of storing those results in a separate table, it actually checks for palindromes like directly within the backtracking process itself, so in place, as the name kind of suggests.
Okay, so we're not pre-calculating and storing anything, we're just checking as we need them.
Yeah.
But wouldn't that make the backtracking part slower then, since we're now having to do those checks every time?
That's a great question, and it could make it slower if we were still checking for palindromes in the same way we did before, like comparing characters one by one from the start and end of the substring. But this optimized approach actually uses this neat trick with 2 pointers to make those checks much faster.
2 pointers, how does that work?
Okay, so imagine you have like a substring that you want to check. You start with 1 pointer at the beginning of the substring and another one at the very end, and then you kind of move those pointers towards each other, comparing the characters they point to at each step.
Oh, so it's like a pincer move, closing in on the middle of the substring.
Exactly. And if those characters match all the way to the middle, then you know it's a palindrome.
Right.
And the nice thing is you're doing this all directly on the original string. You don't have to create any temporary substrings or use extra memory for that DP table.
Okay, this is starting to make sense.
Oh,
So we're still doing backtracking to explore all those different partitioning possibilities.
right.
But we've replaced that separate DP table with this really efficient two-pointer palindrome check. Okay, but how much does this actually save us in terms of memory?
Well, with the DP table, we were using memory proportional to the square of the spring's length.
Uh-huh.
But with this optimized approach, the memory usage is way lower. It's essentially just the space needed to store the original string and then a few variables for our pointers and partitions.
Okay, wow, that's a significant saving, especially for those really long strings.
Yeah.
But I can't help but wonder, like, there's got to be a trade-off somewhere. Doesn't all this cleverness come at the cost of speed?
You're right to think about trade-offs in this case. While the optimized approach saves us memory, it doesn't fundamentally change the time complexity of backtracking.
Okay.
We're still exploring all those possible partitions, and that number can grow exponentially with the length of the string.
So we might be saving memory, but for really long strings, that runtime could still become a problem.
Yeah, that's true.
So I guess it comes back to, choosing the right tool for the job. If memory is like our main constraint, this optimized approach seems like a really good option.
Yeah, definitely.
But if speed is like the most important thing, then maybe dynamic programming with the DP table is still the way to go.
Exactly. It's all about understanding those strengths and weaknesses of each approach and making those informed decisions based on like the needs of your problem.
Absolutely. There's no one-size-fits-all solution.
No.
What matters is you understand those underlying concepts and can, adapt your approach as needed.
Exactly.
That's a really valuable takeaway. Okay, so to recap, we've got these three main approaches to palindrome: partitioning, basic backtracking, dynamic programming with a DP table, and this optimized backtracking with in-place palindrome.
Yeah.
Checking each one's got its own pluses and minuses in terms of, time and space complexity.
And beyond like just knowing these specific algorithms, I think the real learning comes from understanding those general problem-solving strategies they embody.
Yeah, for sure.
So backtracking is about systematically like exploring those possibilities. Dynamic programming is about breaking down problems and storing those results. And this optimized approach highlights how even within a fixed framework like backtracking, there's always room for those clever little optimizations.
I'm starting to appreciate how much thought really goes into this, designing these efficient algorithms.
Yeah, it's pretty cool.
It's not just getting a solution, it's about getting the best solution for your constraints.
For sure.
Speaking of solutions, we've talked about these approaches conceptually, but I wonder if we could go a little bit deeper into how they actually work in practice.
Yeah.
Could we maybe walk through some pseudocode to get a better feel for the steps involved in each approach?
Absolutely. That's a great way to solidify our understanding. So let's start with the brute force backtracking approach, since that's the most straightforward conceptually.
Okay.
So imagine we have this function called partition that takes in the input string, and it returns a list of all the possible palindromic partitions.
Okay, so this partition function is like the brains of the operation.
Yeah.
What does it do first?
First thing it does is check if that input string is empty.
Okay.
If it is, then we've reached the end of a partition.
Right.
So we add that partition to our list of results and return.
Okay, that makes sense. We've chopped up our string into palindromes. We're done with that partition.
Exactly.
What if the string's not empty?
Then we need to start exploring different ways to split it up.
Okay.
And we do this by iterating through the string, considering each possible starting point for a palindrome.
Okay, so we're basically saying, let's try starting a palindrome at the first character, then the second, and so on.
Exactly. And for each starting point, we kind of try extending that palindrome to the right one character at a time.
Okay.
And for each potential palindrome, we check if it actually is a palindrome.
And how do we do that check with this brute force approach?
So we could have this separate helper function called isPalindrome. That takes in a substring and checks if it's a palindrome by comparing those characters from the start and end.
Right.
If it is a palindrome, then we add it to our current partition and recursively call our partition function on the remaining part of the string.
So it's like we're saying, okay, we found one, let's add it to our current solution and focus on partitioning the rest of the string.
Exactly.
What happens if the substring we're checking is not a palindrome?
Then we just move on to the next character and try extending the palindrome from there.
Gotcha.
So this whole process of trying those different starting points and extending those palindromes continues until we've explored all those possible partitions.
That's a really clear explanation.
Hmm.
I can see how it would work, but I totally get why it's not the most efficient approach.
Yeah,
All that checking and rechecking seems like it would really add up, especially for those long strings.
absolutely. And that's why we came up with the dynamic programming approach.
Right.
And we're going to dive into that next, and you'll see how we can optimize things by being a little bit more strategic about how we check those palindromes.
Welcome back to AI.Code.Cast. Before the break, we were walking through that pseudocode for the brute force backtracking approach to palindrome partitioning. It was cool to see how that approach works visually, but we also saw how it can get really inefficient for longer strings because of all those repeated palindrome checks.
Exactly. And that's where dynamic programming comes in to save the day. Remember, the key idea behind dynamic programming is storing the results of our computations so we don't have to repeat them over and over again.
Right, it's like a cheat sheet for our algorithm.
Mhm.
So how do we apply that to palindrome partitioning then?
So we use that DP table we were talking about earlier.
Okay.
It's essentially a two-dimensional array where each cell represents a substring of our input string.
Okay.
And you can think of the rows and columns of that table as like the starting and ending positions of those substrings.
Okay, so if we have the string ABBA, the cell in row 1, column 3 would represent the substring ABBA.
Right.
What do we actually store in each cell?
So we store a Boolean value, either true or false,
Hmm.
indicating whether that corresponding substring is a palindrome or not.
Gotcha. So in that example, the cell for ABBA would store true because it is a palindrome.
Exactly.
Okay, so how do we actually fill in this DP table then?
So we do it systematically. We start with all the single character substrings because those are always palindromes by themselves.
Right.
So we initialize like the diagonal of our DP table with all true values.
Okay, that makes sense. It's like we're laying the foundation for our palindrome knowledge.
Exactly.
Okay, what happens next? How do we start checking the longer substrings?
So then we kind of move diagonally upwards in the table, considering substrings of increasing length. And for each substring, we check 3 things.
Okay.
First, are the first and last characters of that substring the same?
Okay.
If so, is the substring like between the first and last characters also a palindrome? And we can check that second condition by just looking up the corresponding value in our DP table.
Right, so we're building upon our previous knowledge.
Mhm.
If those first and last characters match, and the inner substring is already marked as a palindrome in our table, then we know the whole substring is also a palindrome.
Exactly. And we mark the corresponding cell in our DP table as true.
Right.
And if any of those conditions fail, we mark it as false.
Okay.
And we continue this process until we've filled out that entire DP table.
It's like we're building this map of all the palindromes inside our string.
Mm-hmm.
I can really see how this would save us a bunch of time compared to checking those substrings again and again with the brute force approach.
Yeah.
But how do we actually use this DP table then to find all the valid partitions?
So we still use backtracking, but now it's like supercharged because we can consult our DP table for those instant palindrome checks.
Uh-huh.
So instead of recalculating whether a substring is a palindrome, we just look it up in the table. If it's a palindrome, we add it to our current partition and recursively explore the rest of the string.
That's like our backtracking algorithm has a cheat sheet now.
Exactly.
So dynamic programming doesn't get rid of backtracking, it just makes it way more efficient.
Exactly.
Awesome. Okay, this has been a really fantastic deep dive into palindrome partitioning.
Yeah, it's been fun.
We've covered 3 different approaches: that brute force backtracking, dynamic programming with that DP table, and then optimized backtracking with that in-place palindrome checking. We've gone through some pseudocode, looked at the trade-offs, and hopefully you, our listeners, have a much deeper understanding of how to tackle this classic problem now.
Yeah, and remember, beyond just memorizing these specific algorithms, the key takeaway, I think, is to really understand those underlying principles and those problem-solving strategies.
So sure.
So backtracking, dynamic programming, optimizing for that time and space complexity, these are all concepts that you can apply to a ton of other coding challenges.
Absolutely.
Yeah.
So keep those in mind as you go on your coding journey, and who knows, maybe you'll even come up with a totally new and innovative approach to palindrome partitioning. The possibilities are really endless. Thanks for joining us on AI.Code.Cast.
Thanks, everyone.